Oh yeah, I was wondering. Oh, that's the squash. I thought it would be beer.
Hi everyone. I guess we're going to start. So we are going to start the session with Pravesh. Pravesh is from Princeton and he's going to talk about tensor decompositions. Go ahead.
Let me turn this on. Cool. Okay. Yeah. I want to talk about, well, thanks to the organizers, first of all, for all the work that went into organizing this workshop. It's actually much larger than I thought it would be, so that's great. Thank you for having me. And I want to tell you about tensor decomposition. So 70% of this talk is about, a single result, and 30% is like speculation. Hopefully, you'll like both. And so, like the 70-30 is basically the two worlds I want to talk about. So the first world is like the kind of results that are closer to maybe the interests of most of the participants here, and that is bulk of the talk. And then 30% of the talk is about a parallel line of work on tensor rank and tensor decomposition that seems to have very disparate looking results from this first part. And so like the speculative part is like how might we kind of reconcile these two kinds of results, and in particular I'll ask you a natural open question, even give you like a natural approach, and I don't know how to prove anything about it, and the whole field is wide open. So hopefully you'd be interested in this question that I have to ask towards the end. Cool. Okay, and so the 70% of the talk I'm talking about is based on joint work with Alex Wine, UC Davis, and Ankur Moitra from MIT. Cool. Okay, so let me start with the basics. I'm going to work with tensors. So for me, these are just n by n by n arrays. Okay, I'm not going to work with any geometric meaning of these objects. That's what they're just like n by n by n arrays for me. Each entry is a element of some field. Now everything I'm going to do with them is like some basic linear algebra. So as long as the field is large enough, everything is fine. But let's, for concreteness, think of reals or complexes. Okay, great. Another disclaimer. This is a tensor of order 3, which means that every entry is indexed by a triple of numbers or triple of indices. In general, you can think of tensors of higher order, and everything I say has like an appropriate analog for higher order tensors. But I'll look at only third order tensors because, well, it's easier to work with a single number. But also, it happens to be the most interesting case anyway. So that's what I'm going to focus on. And one final disclaimer. This is like a square or I guess a cube case. All the three modes are equal in dimension. You can think of like the unequal case or asymmetric case, like n1, n2, n3, three different numbers. What I'm going to tell you today does generalize to that setting. It is not without loss of generality, but let's just focus on the cube case. Okay, cool. So I'm going to talk about rank of such tensors. So let's make a definition. I'm going to call a tensor rank 1 if it can be written as a outer product of three vectors a, b, and c. So each of a, b, and c are n-dimensional vectors over the same field. Okay. So what this means is that the ijkth entry of such a tensor is basically the product of ai, bj, and ck. Okay. So if you don't know, if you haven't seen this, I doubt you haven't seen this notation, but if you haven't, that's what it means. So that's a rank 1 tensor. And once you define a rank 1 tensor, you can define rank of a tensor T as the minimum number R, such that T can be written as the sum of R rank 1 tensors. Okay, good, cool. So now there are actually a few different, slightly different looking definitions of rank of a tensor, and they're all kind of meaningful in different contexts. But I suspect that for this audience, basically this is the right notion of rank, and there is like something close related called the varying rank, but maybe those are the two notions that we might in this audience care most about. And so, this is the only notion of rank that I'll deal with in this talk, even though there are other notions of rank that are interesting. So if you want like the name of it, it's like, I think people call it the canonical polyadic rank or CP rank. That's basically the rank we're going to work with. Okay, why are we working with this rank? In some sense, it's a natural generalization of matrix rank, right? Like a rank 1 matrix is an outer product of two vectors. Rank of a matrix is the minimum number of outer products you can write a given matrix as a sum of. And what I did is just lift these natural definitions to tensors. So, it's a generalization of matrix rank. So that's one reason to care about it. But it turns out that there is another reason to care about it, which comes from arithmetic complexity. So this is an observation that goes back to, I guess, Strassen and, the study of matrix multiplication. And this observation that every arithmetic bilinear computation can be seen equivalent to a n by n by n tensor, right? And then, in particular, the rank of this tensor turns out to capture the number of arithmetic operations you need to do to perform this bilinear operation. And so, this notion of rank turns out to capture the circuit complexity or, arithmetic complexity of computing a bilinear, solving a bilinear computation problem. So that's another reason to care about this notion of rank. By the way, I should have said this, I forgot to mention this disclaimer before. I'm not an algebraic complexity theorist. In fact, I think many of you would know much more about tensor rank than I actually can pretend to know. Which means that many of you might have comments, suggestions, I don't know, additions to make during the talk, which you should feel free to do. It will be useful for both me and the audience. Cool. Okay. So, all right. So, that's the notion of rank. And what we're going to be interested in is, can we compute it? Given a tensor T, can you compute its rank? And more generally, can you decompose a tensor into, rank number of rank 1 components? Make sense? Okay, great. So, it's a natural generalization of matrix rank, and you know that matrix rank computation is obviously doing everything, including powering language models or whatever. So clearly there is maybe some interest in studying the tensor generalization without any other specific motivation. But I do want to give you one additional motivation, just in case you haven't seen this one before. Okay, how many of you heard of method of moments before? Okay, I guess most of you have, so I'll be quick with this, okay? So the idea is that you can learn the parameters of a statistical model given sample access to the model by somehow, decomposing its moment tensor. And the idea is that moment tensors can be efficiently computed from samples. So you could compute this object, then, if you could somehow decompose the tensor, you would be able to get a handle on the parameters of the model that you're interested in. And if this looks very abstract, by the way, this idea goes back to more than 120 years ago by Pearson. So it's like a beautiful idea, and it has had like more than 120 years of impact, so to speak. So I'm going to give you like one example. Sorry, was there a question? Okay. I'm going to give you one example of this, just so that you have a concrete thing to play with, and I'll also use it as an excuse to observe like a couple of different properties that we might care about. So this is this problem of learning mixtures of spherical Gaussians. Okay, what it means is you're given access to a mixture of k Gaussians, samples from a mixture of k Gaussians. What that means is that every sample is chosen as follows. You toss like a k-headed coin, and if it lands on I, uniformly distributed, if it lands on I, you will draw a sample from the ith Gaussian. Okay. Now, all the Gaussians have the same covariance, identity, but they have different means. So mu1, mu2 up to mu sub k. And these are just arbitrary vectors in n dimensions. Okay? And of course, they're not known to you. Your goal is to take input, a sample, an IID sample from this model, and figure out what the mui's are. Okay? Problem makes sense? Now, there are multiple approaches to solving this problem, and there's a lot of literature on it, but I want to tell you one approach that fits very well with the agenda of the talk, which is the method of moments. Okay? And so this observation goes to this very nice paper of Xu and Kakare from 15-ish years ago. They observed the following, that if you look at the third moment tensor of this distribution D, then after some mild tinkering with it, it basically looks like a tensor with rank k, and the components are the mui's. Okay? And this tinkering is actually kind of easy. The first term, if you look at it here, is just the third moment of the distribution D. This thingy is, it's some, okay, so let's say maybe interpret this object here. This is the average of the means tensored with identity, And sim means symmetrized because there are like 3 different positions you can put this average of mu i's in, like first mode, second mode, or third mode. And depending on where you put it, like there are 3 possible things. Symmetrization just means average over the 3. Okay. And so what this statement means is that if you somehow subtract this symmetrized whatever, like product of average of the means with identity from the third moment tensor, you are left with basically the tensor with components mu i's, rank k tensor with components mu i's. Okay, this observation is, by the way, trivial to verify. Once I claim it to you, you just write it down, and it's just simple algebra to check that it's true. Okay. Moreover, the left hand side is very easy to compute given sample access to D. Okay. You want to compute this, you can take the empirical third moment of samples from D, and you get some close enough approximation to the first term. The second term is also easy to compute. The only non-trivial thing is how do I get a handle on this thingy, but that's just the mean of D. So just like average a bunch of points from D, and you got an estimate of sum of mu i's or average of mu i's. That's it, okay? So you can get like a decent approximation to this guy, like by making more and more samples or whatever. So you can get like a, up to some small error, you can get access to this right-hand side. And so now if you had tensor decomposition algorithms, you could apply it to this right-hand side and learn the means, okay? Now there's an issue that I only have noisy sample access. Let's ignore that. Maybe I'll mention something about it towards the end. Yeah?
Even if you don't have noise, you can't compute the expectation, right? You're really getting something that is a sum and there's an error.
Sampling error,
right? There's an expectation, right? Like
you mean sampling error, right? Like just the empirical mean of x tensor 3 may not converge.
It's different than that, right?
Yeah.
By a lot in terms of rank, or can you always have
by a lot in terms of rank, but by a small amount, let's say in Frobenius norm, or you have to put norms here, right? Like it's not going to be, yeah. Good question, right? It's non-trivial, but let's ignore that part because there's a different, bigger problem here. Okay. So you want to say that I'm done. Oh, sorry. Go on.
But you cannot just subtract 2 approximated values to get another approximation, right?
Yeah, so what you're asking is like, what's the error going to look like? So I'm going to have some additive error here. I'm going to have some additive error here. The property of these additive errors is that they go to 0 as the number of samples go to infinity. So I'll take like large enough number of samples that the error becomes tiny enough.
Oh, so you are only considering the additive error rather than multiplication?
Let's say additive error, yes. I'm considering nothing to be honest, but let's say we are looking at additive error, yeah? Okay, so okay. Let's say, you got infinitely many samples and you got like the left-hand side exactly. Suppose we did that, right? Even then, you're not quite done. Are we done? Why not? Say you could compute this object exactly. Are we done?
We cannot compute the rank decomposition.
Let's say I gave you an algorithm for rank decomposition. Correct. That's the issue I want to point out, which is that even if you had an algorithm and even if there was no noise, there could be a different rank A decomposition of the same tensor. You have no reason to believe that the only rank A decomposition happens to have mu i's as components, right? And so this brings us to a very important issue about tensor decompositions. It's like, when are they unique? And you can see that we do care about the case. We do care about understanding when they are unique. In particular here, it matters whether I can compute the mu i's or not. Okay? Does it make sense? You're all with me so far? Okay, great. So let me, point out something obvious, that this is a non-trivial idea. Like, a priori, if we carry over our intuitions from matrices, we might actually, assume that it's never going to be unique, or like basically, like generically, things cannot be unique, right? For matrices, if I have like a rank decomposition, let's say sum of vi transpose, think of it as like, VV transpose for a matrix V where the columns are the VIs. Then, I can basically put in any orthogonal matrix in between, UU transpose, that's identity, and I get a new rank decomposition after this rotation. And, there are infinitely many equivalent rank point decompositions of a matrix in that sense, right? So, if the same applied to tensors, we are in trouble in the sense that, this approach would be completely bogus. I would never be able to figure out the means by tensor decomposition, even if I had an algorithm for it. Except we get lucky. It turns out that tensor decompositions do behave quite differently from matrix decompositions. They are generically unique, and I'll try to justify the statement in the next 5 minutes. Yes?
So why did we start with the third moment? We could have taken the second moment or the fifth.
Yeah. There was an answer already?
This is not unique if you take
Yeah, so the first and second moments are kind of like, the first moment is like, entirely a function of just the average of mu i's. So clearly you cannot determine mu i's from it. And the second moment is a function of just the sum of mu I transposed. So like, let's say, you could, this is like some kind of a normalization. You could just assume that sum of mu I transpose is identity in some subspace and sum of mu i's is 0. So, that doesn't give you enough information, and now, it's like completely, like no extra information from the first two moments. So you could deal with higher moments, but 3 is like the smallest number where you can hope for some action. So yeah, we are just looking at the minimal algorithm, so to speak. Good. Any other questions so far? Okay, great. All right. So so I guess the last thing I wanted to say, okay, so I'm going to justify what this generically unique, etc. means, and I'll come back to, whether we actually did anything meaningful in this exercise so far, okay? But that leads us to this question. Okay, so that was a uniqueness issue that we discussed, but we still have this question of whether we can compute these decompositions efficiently, right? That was the other question we started with, and at least we have some motivations for doing this, and we have some inspiration. Matrix rank is easy to compute. You might guess or hope that tensor rank would be easy to compute, but not so great for us. Tensor rank turns out to be NP hard, and there are like even in some sense you can even prove this result somewhat robustly in the sense that you can have some kind of gaps and so on. So that's bad, right? Oh yes.
Just a small question. I was confused. Can you please go back?
Yes.
The right hand side in my mind is a sum of k things.
Yes.
And on the left it's one thing. So some normalization is missing. It's not in the right.
The left hand side is a expectation over.
So, but it's like one thing, and on the right it's a sum of all of them. So
I'm missing a 1 in k. You're absolutely right. That's probably is the question, right?
Yes.
Yeah, I'm missing a 1 in k. It should be average of mu I tensor to the 3 and not. Yeah, you're absolutely right. Good question. Yes. Yeah, I made the slides this morning. Good. Okay. So So okay, good. So tensor rank is NP hard, but sometimes so we use this the following kind of phrase is overused, that NP hardness only affects pathological instances. But I think if there is one situation where it is going to be well justified, it is this. Okay. In fact, like this talk is basically going to argue to you that in many senses, tensor rank being NP hard is much less of a barrier than you might imagine at first. Okay. And so that's the hope, and I'll try to show you how it might pan out. Okay. Good. Okay, so what I want to tell you now is, I'm going to give you a baseline algorithm. I'll give you an algorithm for tensor decomposition. It's an old algorithm. It's not my work. It's not even Yenrik's work apparently. It's actually a paper of Harshman who somehow credited to Yenrik, and it's complicated. But I'll tell you this Yenrik's algorithm of the 1970s. So it's both an opportunity to justify the previous statements, give them some concrete meaning, and also think of it as a baseline. And then I'll come back and tell you how we can improve on it. Okay. All right. So let's say our goal is to take a tensor, and let's say it has some rank decomposition like this: AI, BI, CI. These need not be unique. There might be other rank R decomposition. So far we've said nothing. Okay. So given such a tensor, our goal is to decompose it, and we will like a min rank decomposition. So decompose it into R rank 1 components. Okay. Good. So, because, my goal is not to really teach you the details of this algorithm, I'm going to be sloppy and make all the assumptions that help me. So let's first of all simplify notation. Let's just assume that AI, BI, CI are all equal. Okay. Why carry around 3 numbers or 3 different, letters? So let's say it's like AI tensor to the 3. Okay. The same algorithm works. It's just easier to write down here. Good. Okay. So we are going to work with this. And the key idea is that I'm going to compute some matrices from the tensor, and these matrices will help me figure out what the AIs are. Okay. So the idea is to view the tensor as n slices. You can slice it along any mode. If you take any mode of the tensor, and you have n slices, t1, t2, tn, and these contractions produce matrices by taking these ti's and taking a linear combination of them. So I just multiply them by some coefficients, add them all up. This gives me a matrix. Okay. So mg is the matrix where the coefficient vector happens to be g. That's what the definition is. So mg, the matrix entry at d comma e, is going to be just t d e f summed over with coefficients g sub f. This is I'm thinking of the last mode as the slicing mode, and I'm just summing them up with coefficients gf. Does it make sense? Okay. So I'm going to write this as So you can see that's equivalent, of course, but I'm going to think of it as mg as sum of AI transposed with, the weight being AI in a product G. By the way, if you had AI, BI, CI, then the weight would have been CI in a product G because I'm like averaging out the last coordinate. Okay, good. So I'm going to think of this matrix as A, DG, A transpose, where A is the matrix with AI as columns. DG is the diagonal matrix with, the ith entry being the inner product of AI and G. And A transpose is, of course, the transpose of A. Okay? Still okay? All right. So that's my MG. I can compute similarly an MH, like basically the same idea, but with a different coefficient vector H. Okay? And then here is a main observation of Yandex algorithm. If I compute mg times mh inverse, okay, we'll come back to this question of whether they exist and so on, but let's pretend they exist for a second. If I compute mg times mh inverse, I can basically, explicitly compute what this expression looks like by just plugging in those formulas above. Okay? So what am I doing? Mg is A dg A transposed. Mh inverse is like A transpose inverse dh inverse A inverse. Multiply together, A transpose and A transpose inverse cancel out. So I get A dg dh inverse A inverse. Okay? Now for this operation to have made sense, dh should not have 0 entries on the diagonal. Okay? So we're going to assume that. For this operation to make sense, A should be invertible, which is equivalent to saying that AI should be linearly independent. We're going to assume that. Okay? So as long as AIs are linearly independent, therefore R cannot be more than N, and DG and DH are full rank, no 0 entries on a diagonal, this operation makes sense. And then once you look at it, you observe that what I have over there is a diagonalization of MG MH inverse, right? Because I have A diagonal matrix, A inverse. Okay? So, I have a matrix with a diagonalization, so I can basically compute this diagonalization with eigenvalue decomposition. Oh, yes?
Just make a comment. I mean, people in algebraic complexity theory, when they think about tensor rank, they think about an R that is much bigger than N.
We're coming to that.
One should say that this is, you think of a situation if R is maybe considerably smaller than N, and then this works. Otherwise...
We are going there. That's why I said it's the baseline.
Good.
Yes. Yes, we are going to R bigger than N very soon, in like 2 minutes. Okay?
By the way, of
Oh.
fields, you could have just used one G and that's it, right? You compose A dg A transpose.
No, because it's not an eigenvalue decomposition.
No, but it's a symmetric matrix.
But it could have multiple decompositions of that sort. A is not orthogonal matrix, right? Like the columns are not orthogonal in general. Yeah. So it's a good point. Yeah, like even over the reals, I do need... so basically this, under the hood is just simultaneous diagonalization of 2 matrices. That's what I'm doing. But, just an explicit representation of the algorithm you will use for simultaneous diagonalization. Okay, good. So, I wrote down an explicit matrix, very easy to compute, very easy to write down. I know it's, diagonalizable, and, the eigenvectors of this matrix basically correspond to AIs. Okay? So I can compute them. All I needed was that DG and DH should be full rank, and that's a probability 1 event if G and H are like chosen randomly. Gaussians don't matter. Choose any continuous distribution, that's fine. Okay? Does it make sense? I mean, I'm kind of quick about this, but I'm happy to take any questions if they are there. Okay, good. So that's it, right? That's the algorithm. Good. Okay. So, I just want to note that MG MH inverse need not be a symmetric matrix. Not all symmetric matrices are diagonalizable. Not all asymmetric matrices are diagonalizable. But, this one is because I produced the diagonalization. So we got lucky. Okay? Good. All right. So let's, summarize what we did as this theorem statement. It's Yandex algorithm, but it's in Harshman's paper. There's a polynomial time decomposition algorithm, the one I just gave you, that succeeds whenever the components are linearly independent. Okay? So in particular, handles rank at most n. Okay? And that's it. Okay? Good. So actually, the same analysis that we did proves something a little bit more. That the min rank decomposition is unique. Notice that uniqueness can, when I'm computing eigenvectors, I can't compute their lengths. So it's only unique up to scaling. And I can't tell you which one is first and second eigenvector. So it's unique only up to permutation. But that's what I mean by uniqueness here. And our analysis basically established that up to scaling and permutation, AIs are the only components of a min rank decomposition. So this analysis also established uniqueness. Still okay? Okay, great. So it turns out that this is not an accident. All known algorithmic results, at least the ones I know, when they succeed in tensor decomposition, they actually also end up proving uniqueness of the decomposition. I don't have a great explanation for this, but this is an audience to ask this question to. So, if you have this question, ask someone in the audience. I don't know what to say about this. Okay, great. So that's the Harshman result. Now, let's, observe one thing about it, because that's going to be a nice setup for going forward. All we needed for the success of this algorithm was linear independence of A1, A2, AR, right? And so I'm going to call this as an example of a generic property, okay? In general, if you don't already know what a generic property is, just think of like, a property being generic if the only way it fails is when the input parameters form the zero set of a non-trivial polynomial, okay? What would the polynomial here be? Just so that you're all with me. Yeah, like, the determinant, right, for example. Yeah, okay, good. Yeah, just full rankness, right? Like that's what we're checking. Good. So yeah, so this is the generic property. And one implication of this is that, if you take any continuous distribution, then this property must hold with property 1. Okay, just because of like how polynomials behave. So, you can see, this as like some kind of a justification to the statement I was making earlier. That, on the one hand, tensor rank is NP hard, but at least for rank less equals n, really like, the hard instances are really truly pathological in this precise sense. Okay, for at least rank at most n. Okay, good. All right. So let's go back to Peter's question, the interesting regime. We already know how to do, under pretty minimal assumptions, the decomposition of tensors with rank at most n. So we ought to ask what happens when rank is bigger than n. And that's going to be the main topic of interest going forward. Okay? For some reason, and I again don't know the reason why, Peter is the right person to ask, that this regime is called the overcomplete regime. I don't know why n is like the standard of completeness, but it is what it is. So we're going to work with the overcomplete tensor decomposition problem from here on. Okay?
How far will we go?
Not too far, as you'll see. Yeah. We'll see. Yeah. Good. Okay. So let's so Peter had some fears, and let's make Peter's fears precise. Okay. So it turns out that algorithms for overcomplete tensor decomposition turn out to have consequences that on the one hand we like, but on the other we also feel are kind of difficult. So they are like usually, this complexity theory way of like, it's too good to be true. Like, because it will solve some problem that we believe is hard, so probably it's going to be hard. That kind of stuff going on here. So let me like, mention this point here. So, here is a corollary of the algorithm that we just studied, that I can explicitly construct for you a tensor of an n by n tensor of rank n. Okay, and how would I do that? Well, just take any linearly independent vectors, produce a tensor with those components, and then everything we just argued shows that the rank of the tensor is exactly n. Okay? Why am I saying this? Because you can ask how large can the rank of a n by n tensor actually be? Turns out random tensors have rank constant times n square, and some constant times n square is an easy upper bound, right? Just by like some matrix rank thing. So even though the rank of a tensor can be as large as quadratic, this algorithm only allows us to explicitly produce a tensor of rank, exactly n. So the question is, can you do better? So it turns out that, for some reason, this turns out to be a difficult problem. And, there are various intuitions for this, but there is like one pretty precise result. Randraz proved about, I guess, 16, 17 years ago, that if you explicitly construct tensors of large rank, and I would be agnostic about how large here, then in fact you get arithmetic circuit lower bounds, or arithmetic formula lower bounds. Okay. Now technically, Ran's result really applies to tensors of growing order, like it doesn't apply to third order tensors, but you can see that in spirit it's like trying to tell you that something's up with constructing rank, explicitly constructing tensors of rank larger than n, even for like order 3. In particular, the best known explicit construction is by people in the audience, or at least, oh my bad, sorry, I misspelled for jet lag. Sorry, I know your name. So the best known construction, explicit construction of a tensor, n by n tensor of large rank, The record is 3n. That's the number to beat. And that's actually from 15 years ago. Okay? So this is, did I channel your fear correctly? Did I, like you were asking about, how far am I going to go? It seems like, 3n seems like, if I go beyond that, something very nice happens.
I was guessing 3.5.
I like that you're guessing 3.5. Then I have something interesting for you. Okay, so.
But GF2 they are better.
Say it again?
Over GF2 they are larger, lower boundary.
But we are on over.
Yeah,
Oh.
we're over the weight.
Excellent. See, I told you. The audience knows more than me here. So, do you know the reference?
Yes, but no.
I'll ask you. Yes. Sorry to put you on the spot. You're not giving the talk. Okay. Good. Okay. Good. All right. So, let me tell you what we know about this problem. So we saw lots of connections, what we know about it. So let's, see what can we do about it. So first we saw algorithms for tensor decomposition seem to imply uniqueness of tensor decompositions, like explicit conditions on the components that guarantee uniqueness. So you can ask, let's maybe ask uniqueness question even before algorithms. And people did that, and there's a famous result of Kruskal, which I think Peter is probably referring to, which says that there's a deterministic condition. I won't write it down for you, it's kind of clunky. There's a deterministic condition that is easily satisfied by generic AIs, under which, if a component satisfies this condition, then up to rank 3/2 times n, or 1.5n, the tensor rank decomposition is unique. Okay? This makes sense? So this is like, in this overcomplete regime, generic components that satisfy, a deterministic condition, like cleanly describable condition, if the AI satisfies that condition, it's going to be like some kind of an upgrade of linear independence, right? Like linear independence doesn't suffice. So it's going to be some upgrade of it. Under that condition, you can have uniqueness beyond n up to, 1.5 times n. This is called Kruskal condition, and I'm going to keep calling it Kruskal condition in this talk, okay? So you can ask, so by the way, this condition is not efficiently checkable. And certainly we don't know any decomposition algorithm that go from this condition, but let me tell you what else happens. Okay, so you can ask, can you go to Kruskal, or can you at least do anything for tensor decomposition in the overcomplete regime? For the longest time we knew nothing. Then I guess 6 years ago, Chen and Rademacher showed that we can do something. So if you have rank n plus L generic components, then you have a poly n exponential in L time algorithm to compute such a decomposition. So you can think that maybe I can do n plus log n. Okay, so it's like additive bump over n as opposed to multiplicative. I don't know which one you like. Maybe probably you would like multiplicative ones better, but it is what it is. Okay, and then I guess 2 years ago, Pascal Coiran did this amazing result where he proved that you can efficiently decompose tensors and also establish uniqueness for rank up to 4/3 times n.
Is it for generic?
Yeah.
For generic. Okay.
Yeah. Everything is generic. Yeah. On this page, everything is generic. So this is great. For the first time, we have our standards for genuinely overcomplete are obviously low because we were starting with additive thingy, and now you say, oh, we can at least do multiplicative constant bigger than 1. So that's kind of nice. But we haven't beaten Kruskal yet. So you could ask, can we beat Kruskal? And by the way, so Pascal's result actually has a very nice idea, which you can think of as a nice generalization of Jendrik's algorithm, which is one reason I told you about it. It's the idea of commuting extensions. Let me not tell you about it right now, but you can ask me in questions and I'll describe it. It's a very beautiful idea, but I feel like I'm slower than expected. Here is what we prove. We show that in fact there is an algorithm that goes basically arbitrarily near 2 times n, and the constant 2 is nice, in particular because it beats 1.5. Okay, so thank you for setting up the right 3/2 n benchmark. Otherwise, it would have what are we doing?
Expectations.
Yeah, setting the right expectations is extremely important.
Are these all under the same deterministic condition, or the conditions are changing?
The conditions are changing, right? All of them are generic conditions, but they are not the same conditions. Yeah. In fact, for example, the question of efficiently decomposing under Kruskal condition still remains open.
No, this guy here has an algorithm.
Oh no!
Yeah, it's no longer open.
Oh, my bad. Thank you.
Let me clear the context. So, if you just assume critical condition,
Yes.
then our result is more like Chen Rademacher, but just assuming critical condition.
Okay.
Nothing else.
Okay. Okay. Good. Okay. So you can do something under the critical condition. Okay. And ask Vishwas for more. Okay. So we can actually do some asymmetric generalization of this result, but let me not read it out to you. The punchline here is that this is a completely elementary analysis. In fact, the proof looks pretty much like the proof that Rohit did for his bipartite patching. Write down the matrix, muck around with it, and prove its full rank. That's what we did, okay? And I think I was telling Vishwas, I know very little algebra, so this is all I can actually possibly do. So if I'm an author of this paper, this is the only way it could possibly work. Thankfully, we did manage to make it work. And so, the idea is Koshul-Young flattenings. The name looks scarier than it is. I'll tell you what this is very soon. Okay, yeah, so we can go beyond crystal conditions. So that's, I guess, somewhat nice. Cool, okay. Any questions? I'm going to tell you basically the idea now. Yes?
Is there a kind of a other direction, like all the uniqueness proofs are algorithmic now?
Well, crystal is not, for example, right?
I see.
I mean, it's somewhat algorithmic, as Vishwas said, but maybe not in the strong sense.
Algorithmic, but not efficient. Yeah.
Okay, sorry.
Efficient algorithm.
Yeah, algorithm. Okay, I interpret it as efficient. Yeah.
In any of these conditions, what happens when you go just beyond the whatever threshold you have? Like, so at 1.5n, if you just, I don't know what just means. Is it epsilon n? Is it plus
It's
1?
it's a good question. I mean, they're rank arguments. So some matrix becomes singular. So nothing works basically.
But do we have a sense of whether there are too many? So maybe the answer is maybe this is the right bound, and maybe
yeah, it's a good question. You can ask, for example, the uniqueness breaks, but can you still give a list decoding kind of guarantee? It's a good question. I feel like Madhu has asked such a question in the past, or I have been told by somebody else that Madhu has asked this question in the past, but I don't know an answer. So again, another question to an audience member. Okay, great. All right. So, any other questions?
Wouldn't you expect uniqueness up to rank almost n square?
Yeah, so good question. So, of course, for random components or generic components, it's just true that uniqueness holds. But I think we would like explicit, deterministic, maybe clean, simple, writable conditions under which uniqueness holds. Because, we want to somehow analyze some algorithm. So,
I mean, just in general, in principle, you could hope for an algorithm that recovers one n to the 2 minus epsilon.
Yeah, you're saying, is there any reason to believe this doesn't exist? No, I don't think so. I mean, we'll have great circuit lower bounds, but we should. So, yeah, you're right. There is no reason to, I don't think there is any NP hardness or whatever that applies to the generic regime, for example. Yeah.
How do these change with higher order tensors if you go from 3 to D?
Higher order tensors. So you can get, basically some other constant, but, I don't remember the constants. Yeah. Okay, good. So let me tell you the main idea, okay? By the way, how am I doing on time? Who is my chair?
I'm in your chair, so 20 minutes.
Okay, good. Yeah, okay. So I'll be faster now. Okay, so, the main idea is kind of wacky, okay? And it actually is not our idea. It's an idea from a paper of Neeraj and Ankit Garg and Chandan Saha. I'm going to describe this idea. The idea is that, we'll solve the rank detection problem as opposed to, rank computation or rank decomposition, okay? What does rank detection mean? Basically, I give you a tensor, and your goal is to certify that the rank is at least R, or let's say equal to R, okay? So that problem is, in some sense, from our discussion so far, you would imagine, and you would believe me, I guess, that this, feels necessary. Like any decomposition algorithm, at least of the kind that we're considering, would end up producing a certificate of rank, okay? The kind of uniqueness conditions, etc., that we're talking about. So it seems necessary, but we're going to try to do this special case first. Now, the idea is, or why you would care about it, why you might expect you have some mileage for this, is because such certificates arise naturally if you want to construct explicit tensors of high rank. How are you going to prove that the rank is high? Well, you're going to do some certificate. Let's try to see what certificate you're using. Let's hope that certificate helps us design an algorithm. Okay, that's the idea of this whole approach. And this general idea I'm going to call certificates to algorithms, right? Proofs to algorithms. And in the context of tensor decomposition, or I guess problems like tensor decomposition, I remember first seeing it in this very nice paper of Ankit Garg, Neeraj Kayal, and Chandan Saha. Basically, they observed that various lower bound proofs have to come up with certificates of circuit size lower bounds, and in particular, let's say like for bilinear computation, rank lower bounds. And they asked, can I use rank, like the measures we use to lower bound rank, to actually do circuit reconstruction or learning, or decomposition in our case? That's basically what they asked, and they proved results like this. So for example, they start on the shifted partial derivative certificate and actually get some algorithms. Actually, this idea, at least philosophically, is more general. If you know this SOS proofs to algorithm method or SOS certificates to algorithm method, it's also actually quite similar, except there the certificates are SOS certificates and they're not rank certificates. Okay, so that's going to be our idea. Okay. And now, how will we detect rank? It turns out that, we don't know all that much. Even though, we know lots of fancy algebra, we don't have great tools to certify rank. Really, we have one trick up our sleeve, which is to somehow reduce to matrix rank. Take a tensor, make a matrix out of it, and somehow relate the rank of this matrix to the rank of the tensor. That's the best we got, okay? So, let's formulate it as the following definition. I'm going to call a linear map, I'm going to call a map from T to a matrix M of T, a rank detector gadget, if it has the following property. One, its rank should be subadditive in the rank of T. So rank of, okay, I kind of messed up. Okay, let's go with this. Yeah. So rank of the tensor can be written as some function of the rank of M of T. So it's not f of M of T, it's f of rank of M of T. Okay. So, basically the way you can think of it is following. Think about what happens to a rank 1 tensor. There's going to be some translation between rank 1 tensors and the rank of this matrix. And then, you would assume because of subadditivity of matrix rank that this subadditivity should just naturally hold. Okay. So the rank should not basically be more than additive. The second property says that if the tensor has generic components, then the rank should indeed add. Okay, so I can't hope for additivity in general, but if the components of the tensor are generic, I'm asking that the rank should indeed add. Okay, does it make sense?
Do you think of a linear function?
So in this version, the map need not be linear, but of course, like all algorithms that I know are linear. Okay, I'm formulating this way because I'm going to ask the question of whether nonlinear maps help and say something about it eventually. Yes?
Are you sure the inequality isn't reversed on the first one? Let's
yeah, so it should be, sorry. It's a rank of M of T is at most f of rank of T. That's what you would want. That's the natural subadditivity inequality, and I messed up here. But I'll give you an example very soon to fix my errors here, okay? So, but let me say something more about it before I give you an explicit example. So, turns out rank detection gadgets are not new. Like Strassen was thinking about it 50 years ago. So in particular, in 83, he proposed a very concrete 3n by 3n matrix map. Like take an n by n tensor and build a 3n by 3n matrix out of it. And he proved that it satisfies subadditivity. And he also proved that rank 1 tensors go to rank 2 matrices under his map. But he did not know, or I guess he did not prove generic additivity, so it did not really fully function as a rank detection gadget. This was established by Madlena Persu in her PhD thesis at MIT for R, which is 1.5n, which is suspiciously equal to the Kruskal bound. Okay, and so the story of this project actually begins here. So I was asking Ankur at some point. Actually, I was asking him over several years. Why can't we do tensor decomposition? Beyond n. Why don't we know how to do like generic tensor decomposition? And he would say, well, there is this 1.5n seems like kind of a magic number. It seems to pop out everywhere. It's going to be hard. And I met him 2 times, 3 times. It's going to be hard. It's going to be hard. Then I met Alex Wein. I told him, I don't think this is hard. And then, Alex Wein, basically is the Kikuchi guy, and I am the Kikuchi guy too. So we came up with some construction that seems to work. Okay, that's the story. What we're going to do is come up with a rank detection gadget that works up to basically 2 times n. Okay, that's our goal. And then, of course, I won't get a chance to tell you about it too much today, but, basically you can also use this detection gadget along with some new algebraic primitive to also get a decomposition algorithm. I'll probably try to give you a sense of it eventually. Okay. Yeah.
Is your maybe second was the direction, but do you also prove like border rank upper bound like that?
No.
Because, the way it's written, so it's because the f is.
Yes. It's yeah. I think the inequality is messed up.
Okay.
Yeah. I'll write down a specific map soon. So yeah, sorry about that. Yeah. Okay. So let's try to see what the issue with building such a map is, right? Like let's try to work with the simplest possible matrix you would construct from a tensor and see what breaks, and then you will see at least what the challenge is. Okay. So I'm going to call this. So by the way, the maps from tensors to matrices, when they are linear, they often are called flattenings, and you will see why once I draw the picture. Okay. So here is a way to transform an n by n tensor to a matrix. Okay, which is to basically like merge two of the modes and think of it as a matrix. That's what I'm going to call the trivial flattening. Okay, you can easily see that if I have a rank 1 tensor, it goes to a rank 1 matrix. Okay, so that's great. And you can ask, what happens if I take a rank R tensor and apply this trivial flattening to it? You won't be too surprised, and it's also not difficult to prove, that basically, you rank R tensors go to rank R matrices as long as R is at most n and the components are generic. Okay, so this basically, solves rank detection for R less equals n. And the whole challenge is to come up with a better than the trivial flattening so that you can somehow have like this factor 2 gain that we are shooting for. Okay, good. So I'm going to tell you this flattening. So apparently the nomenclature of this is kind of complicated. So it was studied in the context of matrix multiplication algorithms, and all of the history of it, I guess we learned from J.M. Landsberg. Somewhere it's called the Young flattening, but he convinced us that actually Koshul had it too, so it's Koshul-Young flattening, so whatever. The name doesn't matter because I'm going to describe it concretely to you, okay? So it's going to be a linear map, just like the previous trivial flattening. It's going to map tensor T into a matrix. For rank 1, the map is going to look like do something to the first vector, first mode U, and then take chronicle product with VW transposed. Okay? Now I'm going to describe what this A of U operation is. Okay, this is it. By the way, this is the slide I feel like I would probably be able to get across given the amount of time I have. This is how A of U looks like. Okay? For a parameter P, so it's going to be a sequence of flattenings. So fix the integer P. And then I'm going to give you one flattening for this P. It's going to be a 2P plus 1 choose P by 2P plus 1 choose P plus 1, which is equal, by the way, but I want to think of it this way, matrix. Okay? So the reason I want to think of it this way is because I want to think of the rows as indexed by P size sets and columns as indexed by P plus 1 size sets. Okay, that's what's going on. So A of U is going to look like this. Okay? Chronicle producted with VW transposed. Okay, and you will see in fact that I will use only first 2P plus 1 entries of U. Okay, I'm going to ignore most of the entries of U. Okay, good. Alright, so let me tell you how this map looks like for P equals 1. For P equals 1, if you compute those numbers, both those numbers are 3. So it's a 3 by 3 matrix. In the 3 by 3 matrix, A of U looks like this. Okay, first notice that the support, like the non-zero entries, are precisely in those places where the symmetric difference of the row and the column index happens to be exactly 1. Okay, this makes sense. There are P sets, P plus 1 sets. So the P plus 1 set should be basically one new element along with the P set. That's the only way I have a non-zero entry. Okay, everything else is 0. By the way, this is also 0. Okay, now the entries are signed. You can see that the entries are like some entries of the vector U. So whenever there is a symmetric difference of 1, I want to write down up to sign the entry of the vector U there. Okay, that's what is happening in this matrix. Except there is a sign. Okay, and the sign is like if you think of it as the right in the right way, it's a sign of the permutation that's happening. But let me like concretely describe it to you. Order the elements, like choose a natural ordering of elements 1 through n. Order the elements of, let's say, the bigger set, the column set in some order, and look at the position where I appears. Let's say I'm looking at U3, then look at the position that 3 appears. If the position is odd, put a -1. If the position is even, put a +1. That's it. Okay, extremely concrete. If you've ever seen Kikuchi matrices, it's like the Kikuchi matrix here, which is the reason where we thought it could work. Anyway, yeah, that's the whole construction. Okay. So, just
I guess a small comment.
Yes.
On the first day, we had a talk by Jong-hoon about lower bounds on the tensor rank of the determinant, which also used exactly this method.
Oh yeah. Yes. This matrix, by the way, turns out to be exactly the same matrix that Strassen proposed. So it's not new at all. It goes back at least to 80s. So P equals 1 case is basically Strassen's gadget. It turns out though that once you view it as like this symmetric difference structure, etc., you can define it for any P. And the point is that by going to large enough P, we're going to get 2 minus epsilon. That's what's happening. Okay, even though at P equals 1, we only should get 1.5n. If I raise P, I'm going to get 2 minus epsilon n. Okay, good. All right. So P equals 1 is Strassen's map. Yeah, I guess I told you all of this before. A of u. Yeah. Anyway, I guess. Cool. Okay. Good. So I have to prove 2 claims about this. I'm just going to write them down for you. Claim 1 is what happens to rank 1 tensors. And so you can actually prove it explicitly that rank 1 tensors map to matrices with rank at most 2p choose p. In fact, exactly 2p choose p if the rank 1 tensor has generic whatever vectors inside of it. And this is explicit computation, nothing very difficult. You can see here, by the way, that you can extract a 2 by 2 matrix with like full rank. Okay, so here is a 2 by 2, and that proof works. You just look at the matrix and find a block. Okay, so that's easy. So subadditivity trivially holds because of linearity now. And you have to prove generic additivity, which is like the more interesting statement. So if you are appropriately small 2 minus epsilon times n, then you have subadditivity. That's what this claim 2 says. Okay, I'm not going to prove it for you. The proof is just elementary linear algebra in the sense that it looks basically like Rohit's proof yesterday. Okay, that's all I'm going to say about it. Basically, like, I'm going to look at the determinant of this matrix and then muck around with it until I find like a monomial which always survives, right? Like that's what I'm going to do. So it requires some grungy work, but it's elementary. Okay, that's it. Cool, okay. All right, so, how much time do I have? 7 minutes. Good, yeah, that's great. So, I'll be quick with this slide. You can ask me later if you're interested. I'll tell you like one-line version of what the decomposition algorithm is going to look like. Okay. So I have this rank detection gadget, like this matrix that I built from the tensor. Okay. I know that it is appropriately full rank, like in the the correct way it is full rank because of this generic additivity property. Okay. Now it doesn't even matter what it exactly looks like from the previous slide, but you can see that its form is going to look like this because of like this VW transpose structure. You can look at the matrix. It's going to look like this, like the last 2 modes appear here, and then some function of the first vector appears here. Okay, and so what you're going to do is look at the column span and observe that it's going to be a span of this BI tensor CI kind of vectors. Okay, now just knowing the span is not enough to recover the vectors in general. But the observation is that these components are like, rank 1 when you view them as matrices. Like when you view them as vectors, they're arbitrary, but like, I'm trying to find a rank 1 structured vector in a subspace. You can show that, there are no other spurious rank 1 vectors in the span of BI tensor CIs if the dimension of this subspace is appropriately small. Okay, and then it turns out that there's also an algorithm to do this. Okay, so I won't tell you too much more about this. In the worst case, by the way, like, we have something non-trivial about this problem, but, very bad. But turns out that in a generic case, you can basically have a polynomial time algorithm. Good. Sorry that I'm rushing through this, but that's all I'm going to say about this. Okay, good. So, yeah, okay. So you can ask, can we do better? We did something, can we do better? So with this Koshul-Young flattenings, I won't define it for you, but there's a more general class that generalizes the structure we were looking at. You can prove that you cannot be 2n. So we are basically at the limit. You can ask what happens with linear flattenings more generally. And it turns out that there is a very nice paper of Efremenko, Ankit, Raphael, and Avi that I guess in the paper they claim 8n, but it turns out it's easy to prove 6n with the same idea. So you can show that you cannot beat 6n with linear flattenings, and ours is a linear flattening. So there you are. And then, I defined this, more general nonlinear thing. And, it turns out that you can use it to prove lower bounds. You can show that you can improve, in principle, you could improve something, but not beyond d squared n, if it's a degree d map. So that's, in terms of lower bounds. Good. Okay. Oh, by the way, yeah, you should notice that, if you beat 3n, nice things will happen. You will likely be able to explicitly construct tensors of higher than 3n rank. That would be nice.
You made up for the R.
I'm so sorry. I can't seem to get your name right. Okay, all right. Okay, so I have 5-ish minutes. I'm going to tell you something more. So, we did something, we worked very, very hard, and, thanks to Peter, you also didn't feel too bad about, improving this 3 halves and 2 or whatnot, but let's be honest, what the hell? Right? Like, why are we playing with constant times? And we should really ask, can stronger assumptions help? Maybe I'm just asking the wrong question. Let's make some stronger assumptions about the tensor, okay? So let me tell you what's known about this. If the components are random, it turns out that there is a completely different set of techniques that actually go far beyond constant times n. In fact, they handle nearly n to the 1.5 rank tensors. Okay? So here's the result of Marshy and Strider. They prove that, let's say A1, A2, AR are random unit vectors, and now you form the tensor with AIs as components, and you ask, can I decompose it? And they show that in fact here you can actually get approximate decomposition. You cannot get it exactly in their way. You can get approximate decompositions where the error basically depends on how many components you have compared to n to the 1.5. In particular, the error is little o of 1, so long as the rank of the tensor, the number of AIs, is no more than n to the 1.5. Okay? Does this even make sense? Now, on the one hand, this goes far beyond the regime that we could handle for generic components. On the other hand, it does not yield an exact recovery guarantee, so you might be a little bit worried that, maybe these techniques are just completely different. Maybe they can't say anything about the tensor rank problem, okay? Good, but we can still ask, how do they go so far beyond the results that we could do in the generic setting? What are they doing? What can they exploit? Okay, so let me tell you the key idea, okay? I won't tell you the whole algorithm, of course, but I'll tell you the key idea. For a given tensor, you look at the polynomial t dot x tensor to the 3. Like the natural, there is a natural multilinear form associated. I'm looking at the symmetric version of it, okay? So just like plug in the same vector in all the modes. That's the cubic polynomial, a homogeneous cubic. Their observation, the main observation of this paper, is that if you look at the maximizers of px as x varies on the unit sphere, then they all must be close to the AIs. This statement is very, very false for matrices, but it turns out it's true for tensors of rank order 3 or higher. This is their key observation. And now, you can ask, can I just optimize px? Well, in general, the problem is NP hard, but then you can do the natural algorithmic thing, like take a relaxation, argue that it works, and so on and so forth. Okay? Does it make sense? That's the idea. Cool. Okay. Now notice that such an algorithm doesn't certify rank. Okay? So, you can prove things here, but obviously, you will not improve the tensor rank or explicit construction problem, which is important. I want to now propose an approach. I'm hoping that we'll have an approach that can do tensor decomposition without improving on Michael's problem. Okay? Good. How far can we? So like the natural question to ask is, how far beyond random can I go? This was random components. Can I relax it? Can I go beyond it? Okay. So here is the question I want to pose now. Let's say I want to do over-complete tensor decomposition with smooth components. What does that mean? Imagine starting with arbitrary unit length AIs. And then you perturb each AI by an additive small Gaussian. Okay, so like, this will make them generic, but it's a very specific model of genericity. Okay, some small random perturbation of AIs. And that's my new components. The input tensor is going to be the smooth AIs as components. And I'm going to ask, can you, for this model, do decomposition better than what we know? The best result we know for this is still 2n, the same algorithm I showed you in the first part of the talk. But the question is, can you somehow, go beyond 2n for this specific model? Okay, so I want to tell you one thing. So you can first ask, for this model, can you generalize the ideas of Marshy and Strider? And it turns out you cannot, okay? And there's a very simple reason. The proof of this fact, this main observation, relies extremely strongly on the vectors being approximately orthogonal, which is a property of random vectors, but it's not a generic property. You can't hope for vectors to have it if you just perturb them a little bit. So the whole thing is kind of dead in the water, okay? Now I want to tell you why it's not, and that's the last thing I'll do. Okay, so we talked about this issue of exact recovery and approximate recovery. This kind of a result not only uses orthogonality, but it also only gets approximate recovery. It doesn't really get exact recovery, and that also seems like a problem. Any result that works for smooth component, it seems like it will have to do recovery with arbitrarily small error. So like, let's call it exact recovery, for like, let's say ease of exposition here, okay? It turns out, so you could ask like, first of all, can I at least for random components do exact recovery? If there is any hope of asking this question, I should be able to do that. It turns out you can do it, okay? This is, in my opinion, a underappreciated paper. I don't know how many of you have seen it before. If you haven't, it's my invitation to you to look at it. It's a paper due to Bohdan Kiva and Aaron Potechin. It's a great paper, difficult paper, but it's a great paper, who showed that under the same assumptions of Marshi and Stoddard, you can actually get exact recovery. Okay? And what I'm going to tell you is what they do, 1 minute, and I'll basically suggest the same approach for the smooth tensor decomposition in general. That's the whatever, remaining 2 minutes of my talk. Okay, so I'll briefly describe this approach. For this, describing the approach, I just need two natural definitions. I'm going to define two norms on tensor. They're like the natural norms. You might already know them. If not, I'm going to define them for you. Let's T be a n by n tensor, and now let's work on the reals. I'm going to define the injective norm of T as basically take the natural multilinear polynomial associated with T and maximize it over the inputs over the unit scale. That's the injective norm, or like the natural operator norm of the tensor. The nuclear norm is the dual to the operator norm of the tensor T. Okay, so the nuclear norm of T is basically the maximum possible inner product T can have with any tensor with injective norm at most 1. Okay, does it make sense? Good. Okay, so here is what Kiva and Potechin do. They study the optimization problem of finding a tensor T hat with some explicit components that agrees with the input tensor T and minimizes the nuclear norm. Okay, that's what their algorithm is, and they show that for random AIs, the minimum nuclear norm tensor agreeing with T is basically the tensor with the exact same components. This is how they get exact recovery. Okay. This property, as opposed to the Marshi-Stoddard property, seems in principle you could expect to be true even for smooth components. Okay. So, so my question basically is, can you prove that? And in particular, I want to observe that even though they get exact recovery, they are not certifying the rank of this tensor. If they did, it would have been great, but they're not. They're only certifying that the minimum nuclear norm decomposition is unique, not that the min rank decomposition is unique. And so the approach I'm proposing is take a proxy for rank, namely like nuclear norm or some other norm, minimize it, argue that it is unique for smooth component tensors. Good. Okay, so that's the questions. For smooth AIs and rank, which is like, let's say, some anything bigger than a constant times n, could you actually show that the minimum nuclear norm decomposition is unique? Okay, and then could you algorithmically do it, and so on and so forth. Okay, good. Sorry. So I'll just leave it there.
For these proxies, you get that they basically guarantee uniqueness, but for rank in this regime, we don't have any uniqueness, or is it?
Yeah, so it's a good question. So we don't have any explicit conditions on AIs that will guarantee uniqueness in the regime beyond, 2n is basically the best. Like the theorem I showed you today is also the best uniqueness we have. We have nothing beyond that. Okay. On the one hand, there is no reason for why such a thing should not exist. So maybe we should find one. But if you do believe that tensor rank is hard, or explicitly constructing tensors of high rank is hard, then the point of this last bit was to show you that there is an approach which can allow you to decompose tensors far beyond 2n, 3n, whatever, without saying anything about explicit constructions of tensors of high rank. It even allows, in principle, exact recovery. And so that was the point, that tensor decomposition may be easier than tensor rank in this precise sense for smooth components.
Thank you for the nice talk. I have two comments on the approach using Young-Kothari flattening. On the first day, I talked about recursive Kothari flattening for higher order tensors. So even though you told us that for higher order tensor, the bound of R is known as the constant multiple for the previous one, but I think if one use recursive Kothari flattening, I hope that one can improve the bounds. And the second is, even for third order tensor, very recently, Matheus Micale developed the method nonlinear flattening called chronicle coded flattening. If one use that object, I also hope that the bound can be improved. Yeah, that's my comment.
Thank you. Yeah, both amazing comments and both things that I'm not aware of, so it's likely useful to me.
Okay. First, yeah, thank you for this nice talk. So I have a question, a comment on what you call this Strassen gadget.
Yes.
So the question is, are you sure this really appears in Strassen's paper? So I have actually, I haven't been able to find anything like this at all in Strassen's paper. And anyway, if I would have to give an attribution for this gadget, I would attribute it to Lenzberg and Otoviani probably.
But I thought they attributed it to Strassen, which is the reason.
This whole issue is extremely confused, I think. So the thing is that their method of Kothari-Young flattenings for p equals 2 gives the same lower bound as Strassen, but as far as I can see, it's a completely different proof method. So Strassen uses this method of commuting extensions.
Yes.
He doesn't call it that way, he doesn't give a name to his method.
Yes.
It's a method of commuting extensions.
Yes.
Lenzberg and Otoviani, they have this Kothari-Young flattenings,
yes,
which for some reason give the same result for p equals 2.
Yes.
And so if I want to phrase it as a question, and is there a way to make a more formal connection and explain why you get the same result in a sort of conceptual way?
It's a good question, and we thought about it, and I have a limited answer to this. So, are you Pascal by any chance?
Yes.
Before I refer to you in third person, I should make sure that I can refer to you in first person. Okay, so in our paper, in the appendix, they actually show, so when you analyze your commuting extensions method, there's a natural breakpoint of 2 times n, which is what you're pointing out.
Yes, yes.
And it turns out you can actually prove that the 2 times n is achieved with the kind of tricks we are arguing, which we did in the appendix. So in that limited sense, you can show that I guess the same methods are sufficient to argue that you can reach the limits or whatever. I don't have like a connection beyond that. Although, and there is an email from Avi in my mailbox which I haven't understood yet. He gave me a third reason to describe why 2 times n is apparently the right answer, and it has something to do with like the non-commutative version of these problems. And I can forward you that email and probably also try to read it. But there is a different explanation for why 2n seems to be popping around, in multiple ways. But yeah, sorry, I don't have like a great answer for you.
Thank you.
It's not an algorithmic question, but although your algorithm is 3-2n, our NP hardness kick in much worse. So that's slightly unsatisfactory. So yeah, it's apple to orange in that regard.
It's
We
true.
still don't know if 2n rank decomposition is NP hard.
That's true. Like the best thing is 1 plus epsilon or something, right? Like.
I think it's linear, but the constant is large. But Hastad reduction, if you go through.
Oh, you're thinking of it as a gap problem, like it's like C versus C plus epsilon n, where C is like large constant times n.
No, I think what you're saying is that the Hastad, like the rank hardness for Hastad,
Yes.
is beyond 2n.
Right, yeah. So like if you think of it as a distinguishing problem, then the 2 rank numbers that you want to distinguish between are both like constant times
n
n.
and n plus 1, like the Hastad
Oh.
result, the hardness at the level, like which rank
Yes.
does Hastad prove that the rank is hard? He's
Yes.
saying that the rank is bigger than
Yeah,
2.
so R plus 1, and the R is
Yeah.
bigger than 2n.
Yes.
R versus R plus 1, and the R is bigger than,
Okay. Yeah.
Yeah.
No, you're right. Yeah. It's not clear to me that you will get generic NP hardness because I do believe that there should be algorithms here.
Yeah,
So
it's not a commentary.
Yeah.
It's just unsatisfactory.
And can't you pad these things to make n larger?
So they're competing n and r. If you're padding n, the.
But then the rank is reducing.
So that's the goal, right?
Oh, I see. Okay. Yeah, you're right. That's a good point. No? Why can't you just add zeros and think of the tensor as a larger number of components?
But you're not increasing the R, and you're just changing one benchmark, not changing the other.
It's R and R plus 1, but R can be comparable to N, or could be even tinier than N or maybe that's not what you asked. You want the gap to be larger as opposed, do you want?
The gap is fine. The rank, it's very easy. I think they're complicated. Take a sample set.
Maybe we should have some time for coffee and.
Yes.
It's wonderful to have this discussion here. Great. But let's thank Pravesh and